All right, so now we're going to move on to section 8.3, and we're going to continue studying right triangles. All right, so what we're learning today is still for right triangles. So now, if there's a problem that I give you before, so if I tell you that here, and that this is 35 degrees, and that this is equal to 6, and I ask you to solve for x. Well, we can't do this because it's not a special right triangle, so we can't use any of the things that we learned in section 8.2. And since we only have one of the three sides, we can't use Pythagorean theorem, so we can't use what we learned in section 8.1. But what we're going to learn today will allow for us to solve for this problem. All right, so what our objective and goal for this video is going to be, or not for this video, but for this section, it's going to use sine, cosine, and tangent ratios to solve for the side lengths of a triangle and the angle measures. So we're going to use sine, cosine, and tangent, or trigonometry, to solve for side lengths or an angle measurement. So using these sine, cosine, or tangent, we will now be able to solve for this x. So when you're given a right triangle, if you know certain combinations of side lengths and angle measures, we can solve for any other side or angle. So we would actually be able to solve for all of these missing sides. So we'd be able to solve for this missing angle, this missing side, and this missing side x. So what we will use for this, and we'll talk about this in more detail in the next slide, is we will use what's called trigonometric ratios. All right, trigonometric ratios. So let's go ahead and talk about those a little bit more in detail. So the way that we can create all these trigonometric ratios is if we have different right triangles, and in this case they all have the same angle 32. Well, I know all three of these triangles are similar to each other by the angle-angle similarity postulate. So I know triangle ABC is similar to triangle DEF, which is also similar to triangle XYZ. Because since they have two of the same angle measurements, we know that they will be similar triangles, as one might be an enlargement of the other. So what happens is all of these ratios will be the same, because we know that in similar triangles, that all of our corresponding ratios are the same. So if I were to look at this segment BC, which is opposite of our angle 32. So BC over top of our hypotenuse, in this case AC. I know that that ratio will be the same ratio to this middle triangle as well. That this opposite side, XY, ZY, will have the same ratio if I put it over top of its hypotenuse as well, XZ. So I know that they will have the same ratio. And then I know that it will also have the same ratio to this triangle, where the side opposite of it, EF, and our hypotenuse, the ratio that we create for those. So when we have right triangles, they will always be similar if they have the same angle measurement. So regardless of its size, they will always come back to the same ratio. So these ratios that are formed are called our trigonometric ratios, and we're able to use those to solve for problems that we once could not do. All right, so now let's go through the different types of trigonometric ratios and how we will solve for this. All right, so here we have three different trigonometric ratios. We have our sine, we have our cosine, and we have our tangent. All right, what is important for this is which angle you are highlighting. So if you look from here, we have sine of A. So that means we're going from that angle A. All right, and what our sine ratio is, it is the length of the leg opposite to the angle to the length of the hypotenuse. So from angle A, opposite of angle A would be this side, BC. So we can say opposite leg, or A, over our hypotenuse, C. That is our sine. That's exactly what we just did for all of these triangles. So we were finding the sine trigonometric ratio. All right, now if you notice, when it says sine of angle B, we're highlighting a different angle. So that means the side that's opposite of that angle B is going to be different than the side that's opposite of that angle A. So in this case, it will then become B over C. So as we change which angle we're highlighting, it will change our trigonometric ratio, because it's going to change which side is opposite, and then in this case, which side is adjacent. So for cosine, it is the length of the leg adjacent, so the leg adjacent to the angle, to the length of the hypotenuse. So it's important that you're doing the adjacent leg. So when we highlight angle A, because it says cosine of angle A, so when we highlight angle A, yes, this side BC is adjacent to it, but it's not a leg. That's our hypotenuse. So the only leg that is adjacent to this angle A will be this side, BC. So the adjacent leg, and that is equivalent to this B. So we put it B over top of our hypotenuse. And then when we highlight angle B, so when we're doing cosine of angle B, now the adjacent leg changes. The adjacent leg now becomes this side, BC, which is denoted by the letter A. So it becomes A over top of our hypotenuse, C. Right? So what's important is as we're highlighting our angles, the sides that are opposite, adjacent, and our hypotenuse will change. And our tangent is equal to the length of the leg opposite of the angle to the length of the leg adjacent to the angle. So it's the leg. So in tangent, we're not using our hypotenuse at all. So tangent of A, well, opposite of that angle A is this side B, and adjacent to that angle A, the leg, is this side B. So it will become A over B. All right, so, and then the same thing when we highlight our angle B, we now just need to make sure we change our angle. So opposite of that angle B will be this side B, and then its adjacent leg will be A. All right, so what's important that you understand for this is the opposite and the adjacents can change depending on which side you are highlighting. Now there's one thing that we're going to remember to help us remember this, and you're going to remember Sohcahtoa. There is a song that I'm going to play for you in class pretty much every day for the next 2 weeks. So this way you remember this. Sohcahtoa. And it tells us what's going on. So is our sine is equal to opposite over hypotenuse. Ka is telling us its cosine is equal to adjacent over hypotenuse. And toa is telling us tangent is equal to opposite over adjacent. So Sohcahtoa is something that you will need to remember. All right, so now let's just go through this a little bit more before we start going through some problems. So let's just change this real quick. All right, so remember, if I tell us that we're highlighting angle A, the side opposite of angle A will be this side here, and then the leg adjacent to angle A will be this leg here, so it'll be adjacent, and then our hypotenuse will still be this side here. Hypotenuse never changes. All right, so now if we highlight angle B, the side opposite or the leg opposite of angle B changes. This now becomes our opposite leg, where this now becomes our adjacent leg, and our hypotenuse still never changes. All right, so remember, the opposite and adjacent change depending on which angle we are highlighting. All right, now if you notice, we never, ever, ever start with our right angle. We're never going from our right angle. Every single one that we did was either A or angle B. It was never our right angle. So we'll never highlight that right angle because then in that case we would have two legs that are adjacent, and then the only side that's opposite is our hypotenuse. So we will not ever highlight that angle C. All right, so now let's go ahead and we have two examples we're going to do, and then we're done with this video. The first one is write the trigonometric ratio as a fraction and as a decimal, rounded to the nearest hundred. And the trigonometric ratio that they want us to solve for is tangent of B. That means I need to highlight angle B. Then I need to go ahead and see, well, what is opposite of that? Well, this is my opposite. My leg that is adjacent is going to be this leg here, so there's my adjacent, and my hypotenuse will never, ever change, and that will be here. Tangent, we know it's Sohcahtoa. So our tangent, we know, is equal to opposite over adjacent. So our tangent of angle B is equal to our opposite over adjacent. And in this case, our opposite was equal to 24. So our tangent of angle B is equal to 24. And then our adjacent, because it's opposite over adjacent, is equal to 7. So 24 over 7. And that's our trigonometric ratio as a fraction. And then if we put this as a decimal, our tangent of angle B is equal to 3.43 approximately, because we are rounding it at that point. All right, so using these, we're going to use in a different video that it will allow for us to solve for any missing sides, or we could actually solve for this angle B if we wanted to right now. But we use these ratios. All right, there's one more example that we're going to go through. It's the same thing. We're going to find a trigonometric ratio as a fraction and then as a decimal. This time, it's cosine of angle A. So now our opposite and our adjacent and all that change. Our opposite of this case is now 7. Our adjacent is now 24. And our hypotenuse is still 25. Remember, that one never changes. We're still using Sohcahtoa. So in this case, we're using our ka. So that tells us our cosine of angle A is what they wanted, is equal to our adjacent over top of our hypotenuse. Well, our adjacent we said was equal to 24. So cosine of angle A is equal to 24 over top of our hypotenuse, which is 25. So that is, 25. So that is representing it as a fraction. And now if we want to write this as a decimal, it will be cosine of angle A is simply equal to 0.96. All right, since we're not rounding that, we can say equal to. All right, so this is the foundations of this section. You must be able to write out your different trigonometric ratios. All right, you must be able to do this. You must remember your Sohcahtoa. If you're not able to do this, you won't be able to answer any of the questions in the other videos. All right, so that's it for this video.